Myself, I am Dr. Jntuh. In this class, I am going to discuss with the various Mutex Logs condition, semaphore, bounded buffer problem, and dining philosopher problem. Moving to the first topic, that is Mutex Logs. Mutex Logs is nothing but the hardware-based solution of a critical section problem. The operating system, as we know that they are the simplest tool of operating this different types of software tool in order to solve a critical section problem. Here, the mutex logs are the only solution for a process to acquire a log before entering into a critical section. It releases the log when it exits the critical section. This condition is called as a mutex logs. In this condition, the acquire function and the release function are the most important functions that takes place inside a mutex logs. Whenever the system call is to acquire condition, it performs the section is going to be entered into the critical section. Otherwise, the release condition is automatically performed whenever they are going to exit from that particular condition. This type of mutex logs is called as a spin log. So this is a syntax for the acquire and this is a syntax for the release function. Whenever the acquire section is going to be happen when the system is going to be available with the state. Otherwise, if the condition is in the busy state, wait state, it will move to the false condition. It has to wait in a queue. After that, the acquire state will be occur. For in the release condition, while the condition becomes definitely true, there will be no false condition executed here because the process is going to be left from the particular application critical section. Hence, the condition become always be true in the release condition. Afterwards, the condition is also specified as a spin log condition. It can either move to the acquire section or it may be get exited from the release condition. Moving to the next topic, semaphore. The semaphore, as we know that it is used to solve the various critical section problem. It can be used in the two different types of states. One is a wait state and another one is a signal state. It is used to process the process synchronization value. While in the wait condition, it is termed as signal, and it is while in the signal condition, it is termed as B. For in the wait condition, before going to enter into the critical section, the signal operator is otherwise called as a critical section. This is the syntax for the wait condition. While in the wait condition, the wait operation will execute the particular process. If it is less than or equal to 0, it moves the process to the busy state. While in the busy state, each time the value of the S will becomes the decrement value. Whenever it becomes positive, it will move the particular operation. Whenever it is become negative, it move the operation to the 0. Likewise, the signal is going to be generated. Whenever the signal is going to be increment the value will be readed its argument of yes. There are the two classification problems are there in a semaphore. One is a counting semaphore and another one is a binary semaphore. Whenever one process modify the semaphore value, no other process can simultaneously modify the same value of a particular semaphore. All the modification of the semaphore can be done in the wait state or in the signal state. Counting semaphore is nothing but the integer value can range over an unrestricted domain. Binary semaphore or the integer value can range the value only between 0 and 1. Binary semaphore are usually having a mutex logs, and the counting semaphore will be having the control access of the particular value and find the number of instances over that particular value. How a semaphore usage will be there? Under the two condition, if a process P1 is going to be organized a particular process, it will goes to the mutex condition and enters the critical section. While in the signal condition, it will move to the reminder section whenever the condition is become true. Otherwise, the condition become sleep mode. Mutual exclusion progress, it will be moved to the process first in the mutual exclusion state, after that to the progress state and to the bounded wait state. The process is moved. This is how the semaphore is going to be implement the value with no busy waiting state. Whenever the process is ready and it is going to define a value, it will list how many number of semaphores are there. After that, it waits for a semaphore condition while the S value is become negative. decremented, the value is become lesser than 0, it will block that particular section and move to the critical section. Otherwise, the value is incremented. Whenever the condition is become less than or equal to 0, it will remove the particular process from the list and wake up from the particular process. So these are the two signal condition. One is decremented, another one is incrementing the value of a particular application. As we know that semaphores are used in the critical section problem, it is used to decide whether the particular order of execution will be among the particular process, and the resources that are used are concurrently used by both the process P1 and P2, and with the number of shared resources there. Whenever the signal is going to produce the particular condition in a signal state or in a waiting state, it will move the particular condition. In a semaphore, there are two conditions are happen. One is a deadlock, another one is a starvation. Deadlock is nothing but when two or more processes are waiting indefinitely for the particular resource, the condition will happen here is called as a deadlock condition. Only one has to take that particular application, other has to wait in the particular queue. Otherwise, they roll back from that particular condition. In this case, there are two processes, process P1 and P0 are takes place for accessing the two semaphore value, that is Q and S. It will initially set the value as 1. Suppose a process P0 execute the wait process S, then the process P1 in the wait queue has to wait for a certain amount of time. Otherwise, for a process, signal S and Q is going to be executed in the P0. The process P1 in the signal Q and S state should be wait. What is meant by starvation? Starvation is nothing but an indefinite blocking. A process may never be removed from the particular semaphore queue while it get suspended. Here, an important concept that is called as priority inversion is also used. Scheduling problem will be accompanied always with the lowest priority process that will be giving a highest priority process. The highest priority process will be switched over and process will be takes place is called as priority inversion. After that, in a solution of the particular synchronization problem, we are having three different types of cases. One is a bounded buffer problem, reader and writer problem, and dining philosophers problem. The first problem is bounded buffer problem, which is also called as a producer-consumer problem, is one of a classical example of a synchronization. Here, the producer should produce more number of requirement of depending upon the user. The buffer has to fill all the slots here. The consumer has to get their particular value until the counting buffer value become 0. It will decrement the value of a particular register. So this is called as a bounded buffer problem. Here, the producer has to produce more number of mutex while the buffer is going to be filled, and the consumer has to retry the condition by decrementing the particular value of a register. So the next problem is a reader and writer problem. It allows multiple number of readers to read the file simultaneously. So this will be listed by RR, that is reader is going to read the particular condition. While the reader is going to do a write process, it will indicated as RW. It will not allow the particular process. It has to decide whether the particular solution first reader should give the particular permission of a file, whether they can read and write or not. All the permissions will be given by the reader itself. Whenever the writer going to write a file, no other reading process will be performed in that particular file. For this, the solution is the first the reader and the writer should access the particular semaphore values whenever the counter is become 0. The mutex condition will be logged here. So this can be explained with the help of this syntax. Whenever the reader is going to read the particular condition, the reader has to give the permission for the read-write condition. It will occur the mutex logs until the responsibility of the multiple reader will first read that condition. After that, the reader has to give the permission of the writer to read and write the particular condition. Otherwise, the value will get decremented. If they give the permission, the value will get incremented. If the mutex locks is provided to the particular reader, they will not be allowed to read the particular file and access the particular file in the case of the permission is not given. So this is a solution for the reader-writer problem. Here in the reader-writer condition, the mutex locks has been made for the particular reader. They have to wait for a certain amount of time while the writing is going to be performed. Otherwise, the signal will be, log will be released. It will perform the condition true. It will block all the process that takes place in the writer process. Coming to the next problem, that is dining philosophers problem. Here, the 5 philosophers, they are spending their time by eating in a circular table. The philosophers has to share the circular table in a form of 5 chairs, each belonging to one philosopher. In the center of a table, there is a bowl of rice and the table is laid with the 5 single chopsticks. The condition here is that when a philosopher wants to eat, he has to use the 2 chopsticks, one from the left and another from the right. Whenever the philosopher wants to think, he has to put down both the chopsticks at their original place, and he can be able to think that particular condition for an indefinite amount of time. Okay, for this, the condition here is going to be as a deadlock when there is a starvation occurs between a philosopher. So this is a diagram explaining that a rice of bowl will be in the center and each philosopher is sitting around the table in a circular motion, and each philosopher, if they want to read that particular rice, they have to take their left chopstick as well as the right chopstick. If each of them will take 2 chopsticks, no other person, only 2 of them will be take that particular chopstick, other has to wait in a condition. So this is a initialized to 1, while the chopstick has been initialized as a condition as a 5 chopsticks are there. Each time the value of the chopstick has been incremented, other philosophers has to wait for that particular chopstick to arrive. So this is the only solution for a semaphore that not has been to occur, that the data shared here is also will not be entered into the deadlock condition. Hence, each philosopher has to wait for the 2 chopsticks while the other doing process for a while. So this is a condition here. Several possible conditions of a deadlock problem can be replaced along a table. So we can allow all the 4 philosophers sitting simultaneously at a table. So this will lead to a condition, a deadlock will occur, then one will not be available at the time of that. So we have to use both the left chopstick as well as the right chopsticks, as the even number of chopsticks should be available for the philosopher. Then it will be a best solution for this particular critical section problem. Moving to the next concept, that is message passing. As we know that message passing and shared memory. Message passing is a process. A is going to pass a message to the kernel, as well as a process B is also going to pass a message to the kernel. Here, the message passing can be done directly with the knowledge of a kernel. But in a shared memory, the process A doing a process and going to share the particular process and store it in a shared memory. Whenever the process B want to make a communication, it has to refer to the particular shared memory and take out the particular process and move to the kernel. Thank you.